This is an audio recording for the visually impaired of organic chemistry, Pradeep's book, chapter Diazonium Salt. 10.1 Introduction. Arene diazonium salt were discovered by John Peter Gries in 1858. They have the general formula ArN2 positive X negative, where Ar stands for the aryl group and X may be any anion such as chloride, bromide, nitride, Bf4 negative, etc. Aliphatic diazonium salts are also known, but they are highly unstable. They rapidly decompose even at low temperature, forming carbocations and nitrogen gas. Therefore, in this unit, we shall discuss the chemistry and synthetic application of arene diazonium salt, only particularly with reference to benzene diazonium chloride. 10.2 Nomenclature. Diazonium salts are named by adding the suffix diazonium to the name of the aromatic compound followed by the name of the anion. For example, benzene diazonium chloride, para-nitrobenzene diazonium fluoborate. 10.3 Structure of benzene diazonium chloride. First, molecular formula. The molecular formula of benzene diazonium chloride as determined from analytical data and molecular weight determination is C6H5N2Cl. Second, Gries structure. Gries proposed structure 1 for benzene diazonium chloride in which both the nitrogen atom were directly linked to the benzene nucleus. This structure, however, failed to account for the following fact. First, its salt-like character. Second, displacement of both the nitrogen atom by a univalent atom or group in most of its reaction. Third, its reduction to phenylhydrazine in which only one nitrogen is attached to the benzene ring. Fourth, formation of azo compound by coupling reactions. Fifth, formation of aromatic diazonium salt from penta-substituted aniline. Next is third, Kekulé structure. Kekulé proposed structure 2 for benzene diazonium chloride in which only one nitrogen was linked to the benzene nucleus. Evidence in favor. Structure 2 explains most of the drawbacks of Gries structure 1 such as its reduction to phenylhydrazine, formation of azo compound by coupling reaction, preparation of diazonium salt from penta-substituted aniline, and displacement of both the nitrogen atom by a univalent atom or group. Points against Kekulé structure. Structure 2 cannot explain first its salt-like character and second its instability as compared to azo compounds since both contain nitrogen-nitrogen double linkage. Fourth, Bloom-Strand structure. Bloom-Strand suggested structure 3 for the benzene diazonium chloride in which the nitrogen attached to the benzene ring is pentavalent while the other is trivalent. Evidence in support. It explains all the objection of structure 1 and 2. Structure 3 is further supported by the following facts. First, its reduced solubility in water but not in common organic solvent. Second, its complete ionization as shown by conductivity measurement. Third, the presence of a triple bond as shown by infrared spectroscopy. Fourth, its instability as compared to azo compound. Fifth, it explains the geometrical isomerism as shown by diazotates or diazoates, which are the metallic salts of diazonium hydroxide. The sodium benzene diazoate can exist as a pair of geometrical isomers due to hindered rotation about the nitrogen-nitrogen double bond. 10.4 Preparation of diazonium salt. Aromatic diazonium salts are generally prepared by adding a cold aqueous solution of sodium nitrite to the solution or suspension of a primary aromatic amine in an acid at 273 to 278 Kelvin. Diazonium salts are also formed when aromatic primary amines react with nitrite ester such as amyl nitrite. The nitrite ester needed for the purpose are prepared by treatment of alcohol with nitrous acid. Thus, this process of conversion of a primary aromatic amine into its diazonium salt is called diazotization. General procedure for diazotization. The primary aromatic amine is dissolved or suspended in a dilute acid such as HCl, H2SO4, etc. 3 moles of the acid are generally used for every mole of amine to be diazotized. 1 mole to form the salt of the amine, 1 mole to liberate nitrous acid from sodium nitrite, and 1 mole to keep the reaction mixture acidic enough to suppress the undesirable side reactions such as coupling of the diazonium salt thus formed with the free amine. The amine solution is cooled and a cold aqueous solution of sodium nitrite is added slowly to it at such a rate that the temperature of the reaction mixture does not rise above 278 Kelvin. The addition of sodium nitrite solution is stopped as shown as a few drops of a reaction mixture produces a blue color with starched potassium iodide paper showing the presence of unreacted nitrous acid in the reaction mixture. Too much excess of nitrous acid is generally avoided since it subsequently interferes with the reaction of diazonium salt. The excess of nitrous acid may be destroyed by the addition of urea. Since diazonium salts slowly decompose even at low temperature 273 to 278 Kelvin, they are used immediately after preparation. Evidence in support. This mechanism is supported by the observation that aromatic amines containing electron withdrawing groups such as NO2 are less easy to diazotize. This is due to the reason that the nucleophilicity of the amino group is reduced due to the electron withdrawing effect of the NO2 group as shown below. Such amines can however be diazotized in acetic acid. Conversely, aromatic amines containing electron donating groups at ortho and para position undergo diazotization much more readily than aniline. 10.5 Stability of diazonium salt. Aromatic diazonium salt are much more stable than aliphatic diazonium salt due to dispersal of the positive charge over the benzene ring as shown below. Alternatively, the instability of diazonium salt is due to their tendency to eliminate an exceptionally stable molecule of nitrogen to form carbocations. That is, since the phenyl carbocation is much less stable than alkyl carbocation, therefore aromatic diazonium salt have much more lower tendency to eliminate nitrogen than aliphatic diazonium salt. In other words, aromatic diazonium salt are much more stable than aliphatic diazonium salt. 10.6 Physical properties. Arene diazonium salt are generally colorless crystalline solid highly soluble in water. Many diazonium salts, especially nitrite, are dangerously explosive in the dry state. Therefore, they are never isolated but are usually prepared in situ and used immediately after their preparation. However, certain diazonium salts such as fluoborates are relatively insoluble in water and are stable enough to be dried and stored. Some diazonium salt also form complexes with metallic salt such as zinc chloride. These complexes are generally insoluble. 10.7 Chemical properties. Arene diazonium salt are highly reactive compound. Their high reactivity arises due to excellent living ability of the diazo group as nitrogen gas. They are therefore extremely useful synthetic reagent in organic chemistry. The reactions of diazonium salt are broadly divided into two categories. First, reaction in which the diazo group is replaced by monovalent atoms or group. Second, reaction in which the nitrogen atoms are retained. So first, reaction in which the diazo group is replaced by monovalent atoms or group. Some important reaction of this category along with their synthetic application are discussed below. First, replacement by hydrogen deamination. The replacement of the diazo group by hydrogen or the reduction of diazonium salt to arenes is usually brought about by treating a diazonium salt with hypophosphorus acid at room temperature, preferably in presence of copper 1 salt as a catalyst. This reaction can also be carried out by treating amines with sodium nitrite and hypophosphorus acid as diazotizing reagent. Alternatively, diazo group may be replaced by hydrogen by heating arene diazonium salt with ethanol. This whole process involving the diazotization of an amine followed by reduction of the diazonium salt or replacement of the diazo group by hydrogen is called deamination. It may be emphasized here that during the reaction of diazonium salt with ethanol, two products are usually obtained. That is, one involving the replacement of the diazo group by hydrogen as discussed above and the other by the ethoxy group. The relative amount of the two products, however, depends upon the nature of the diazo compound and the alcohol used. If A1 group is present in the nucleus and ethanol is used, the replacement of diazo group by hydrogen predominates. If on the other hand methanol is used, the predominant product is aryl methyl ether, that is anisole. Synthetic applications. The importance of deamination is illustrated by the following application. First, synthesis of M-bromotoluene. Recall, M-bromotoluene cannot be prepared by direct bromination of toluene or Friedel-Crafts alkylation on bromobenzene due to orthopara-directing nature of the methyl group and the bromine atom. Second is synthesis of 1,3,5-tribromobenzene or symmetrical tribromobenzene. Third, synthesis of 3,5-dibromotoluene. Second, replacement by hydroxyl group, that is synthesis of phenols. Diazonium salt react with water in presence of acid to form phenol. The reaction is generally carried out by adding the solution of a diazonium salt to a large volume of boiling dilute sulfuric acid. The acidic condition minimizes the side reaction involving the coupling of phenol with diazonium salt. Synthetic application. This reaction is especially important since only a few methods are available for the direct introduction of a hydroxyl group into the benzene nucleus. Third, replacement by halogens. Different methods are used depending upon the type of halogen to be introduced. First is replacement by chlorine or bromine, that is Sandmeyer reaction. Aryl chlorides and bromides can be easily prepared by treating a freshly prepared cold aqueous solution of an arene diazonium salt with the solution of cuprous chloride in hydrochloric acid or cuprous bromide in hydrobromic acid. This reaction is called Sandmeyer reaction and gives aryl halide in 60 to 80% yield. It may be noted here that if that is the halogen which is attached to copper enters the nucleus. Next is Cutterman reaction. It is a modification of Sandmeyer reaction in which copper powder and a hydrogen halide are used instead of cuprous halide dissolved in the corresponding hydrogen halide. Yields are often lower than those obtained by the Sandmeyer reaction. Second, replacement by iodine. The replacement of diazo group by iodine does not require cuprous halide or copper as catalyst. It is simply achieved by treating a diazonium salt with potassium iodide or a solution of iodine in potassium iodide. C. Replacement by fluorine, that is Pal-Schiemann reaction. When an aqueous solution of diazonium salt is treated with fluoroboric acid, diazonium fluoroborate gets precipitated. It is filtered and dried. Unlike other diazonium salt, diazonium fluoroborates are fairly stable compound. When dried diazonium fluoroborate is heated, it decomposes to produce aryl fluoride and boron trifluoride. Fourth, replacement by the cyano group, that is synthesis of nitrile. Aryl nitriles can be prepared by treating a diazonium salt with cuprous cyanide or potassium cyanide and copper powder. To avoid the loss of cyanide as HCN, the diazonium salt solution is first neutralized with sodium carbonate and then treated with cuprous cyanide. This reaction is called modified Sandmeyer reaction. Synthetic application. Since hydrolysis of nitrile gives carboxylic acid, therefore synthesis of nitrile provides us with an excellent method for the preparation of carboxylic acid from nitro compounds. 5. Replacement by the nitro group. Nitro compounds are generally prepared by treating an arene diazonium fluoroborate with an aqueous solution of sodium nitrite in presence of copper powder. 6th, replacement by an arsenic acid group part reaction. Treatment of an arene diazonium salt with sodium arsenide in presence of copper sulfate followed by acidification gives an aryl sonic acid. For example, when benzene diazonium chloride react with Na3 ASO3 in copper sulfate, we get the phenyl arsenic acid. Seventh, replacement by an aryl group, that is Comberg-Bachmann reaction. When an arene diazonium salt is treated with an aromatic compound in presence of an aqueous alkali, biaryls are formed. Yield are usually less than 40%. Next is B, reaction in which nitrogen is retained. First, reduction to aryl hydrazines. Arene diazonium salt upon reduction give good yields of aryl hydrazines. This reduction can be brought about by a number of reagents such as stannous chloride, hydrochloric acid, sodium sulfide, sodium hydrosulfide, and even electrolytically. If, however, strong reducing agents such as zinc and HCl is used, the product is an aromatic amine. Mechanism of reduction of diazonium salt with sodium sulfide. The reaction probably occurs through nucleophilic attack by the sulfur atom of the sulfite ion on both the nitrogen atom, forming the dianion of hydrazine sulfonic acid, which is then converted into hydrazine in presence of acid. Second, coupling reaction. Arene diazonium salt react with highly reactive aromatic compounds such as phenols and amine to form brightly colored azo compound. This reaction is known as coupling reaction and is extensively used in azo dye industry. Whereas coupling with phenol occurs in basic medium, that of amines occur in faintly acidic medium at 273 to 278 Kelvin. Coupling usually occurs at para position with respect to OH or the NH2 group. If, however, the para position is blocked, it occurs at the ortho position. If a compound contains both an amino group as well as a hydroxyl group at para position with respect to each other, then the orientation of the coupling reaction can be changed by changing the pH of the medium. The well-known indicator methyl orange, which is widely used in acid-base titration, is obtained by coupling the diazonium salt of sulfonilic acid with N,N-dimethyl aniline. Mechanism of coupling reaction. The coupling reaction between benzene diazonium chloride and phenols or amine is an example of electrophilic substitution reaction in which the diazonium ion acts as the electrophile while phenol or amine act as the nucleophile. A. Coupling with phenols. Since benzene diazonium ions are only weakly electrophilic, therefore strong nucleophiles are needed for the reaction to occur. Further, since phenol is weakly nucleophilic but phenoxide ion is strongly nucleophilic, therefore coupling reaction of phenol are usually carried out in alkaline medium. Role of pH. The pH of the medium plays an important role in the coupling of phenol. As stated above, coupling of phenol is carried out in weakly basic medium as explained above. In the alkaline medium, the diazonium salt first forms diazonium hydroxide, which immediately rearranges to diazo hydroxide, which further reacts with alkali to form the corresponding salt called the diazotate. All these three species in fact exist in equilibrium. Since at high concentration of OH negative ion, the equilibrium will shift in favor of diazo hydroxide and diazoate, both of which do not couple. Therefore, for the desired coupling reaction to occur, the pH must be kept as low as possible in the alkaline medium. However, a too low pH would suppress the dissociation of phenol to phenoxide ion. Therefore, to carry out the coupling reaction, an optimum pH is needed. In actual practice, the optimum pH for such coupling reaction is between 9 to 10. B. Coupling with amines, that is tertiary amines. The mechanism of coupling reaction of diazonium salt with tertiary amine is similar to that of phenol, except that this coupling is carried out under weakly acidic condition. C. Reaction with primary and secondary amine. Coupling of diazonium salt with primary or secondary amine occur in neutral or mildly alkaline medium. Here, NH2 group of the amine first attack the diazonium cation to form diazoaminobenzene. However, when the diazoaminobenzene thus formed is heated in presence of acidic medium, it undergoes diazoamino-amino-azo rearrangement to form para-amino-azobenzene by the following mechanism. Role of pH. In the presence of a high concentration of H positive ion, the lone pair of electron on the nitrogen atom accepts a proton. As a result, the amine exists predominantly in the protonated form as shown below. Due to the absence of a lone pair of electron on the nitrogen atom, the amine is no longer nucleophilic and hence the coupling reaction will not occur at a high concentration of H positive ion, that is low pH. Further, as explained above, two highly alkalinity will also not favor coupling reaction by forming unreactive diazohydroxide or diazoate salt in significant amount. Therefore, an optimum pH of 4 to 5 is employed for such coupling reaction. Thank you.